Our next topic introduces moment of inertia, which is a very important concept in engineering, but usually not introduced in high school. First, there are two types of moments of inertia. One is dependent on mass, while the other is dependent on area. When someone references moment of inertia, they are usually talking about the one dealing with mass. Therefore, the area moment of inertia is sometimes referred to as the second moment of inertia. Now let's talk about what the mass moment of inertia describes. To get something moving, the inertial forces have to be overcome. So the moment of inertia describes how easily it is to overcome the inertial forces based off of the distribution of the mass. So let's look at an example of rotating a long, slender rod. We're going to rotate it around its center point. So we need to draw a z-axis, a y-axis, and an x-axis. You can imagine that rotating it around the z-axis would be pretty easy, since the distribution of mass around the z-axis is only this distance away around the circumference. If instead we were trying to rotate the rod around the x-axis, you can imagine that this would be pretty difficult, since the distribution of mass is much farther away from the x-axis. So from the center point to the farthest point of distribution of mass, this distance is much longer than it was in the z-axis. In this example, because the rod is oriented the same on the x-axis and the y-axis, whether you rotate it about the x-axis or the y-axis, you'll find that the moment of inertia is the same. The most common example of mass moment of inertia are figure skaters and how they bring their arms close to their body in order to increase their rate of spinning. You can also do several other things to this example. You could say that you could make the long, slender rod more like a dumbbell. And now the moment of inertia for all three cases increase. This is because the distribution of mass is now at a further distance away from the respective axis. You can also have another example where you move the point of rotation. So if we have the long, slender rod again, and our z-axis is still through the center, but now our rotation is here at the end of the rod. You can see in this example that the moment of inertia in z is going to be the same as it was in the first case. However, the moment of inertia in x is going to be much greater than it was in the first case over here, because the distribution of mass is now at a very long point away from the pivot point. For the boat design competition, we are not concerned with the mass moment of inertia, but instead the area moment of inertia. Still, this is generally the same concept. Instead of 3 axes of rotation, the area moment of inertia of course only has 2. A typical engineering example concerning area moment of inertia is the bending stress of an I-beam. So if I draw an I-beam, and this is the cross-sectional area, and then I have an x-axis and a y-axis, you can see that my moment of inertia in x is going to be much greater than my moment of inertia in y. This is because the area that has to fold on my y-axis for my moment of inertia in y is this area right here. Even though some of my area is a good distance away from my y-axis, the majority of my area is laying right next to the y-axis, and therefore the distribution is not that great. When I look at my x-axis area that has to fold on top of my x-axis, it's all of this area instead. And therefore, this area is a very good distance away from my x-axis, which makes my moment of inertia in x much greater than my moment of inertia in y. For the purposes of the boat design competition, the area moment of inertia of the design waterplane is used to determine the boat's stability and the ease of the boat rotating through its pivot point. So imagine that we have a center line. So imagine on this center line that we have two boats. First we're going to have a monohull, and then we're going to have a catamaran. Now let's say that the area off of the center line of the monohull is the same as the area of one side of the catamaran. This would mean that the moment of inertia of the monohull is less than the moment of inertia of the catamaran, because the distribution of area here is less of a distance away than the distribution of the area for the catamaran. There are a few things to note about the moment of inertia of simple water planes like this. Since the water plane areas are simple geometric shapes, the moment of inertia at the centroid can be found easily from derived equations. Second, whether the moment of inertia is taken at the center of flotation, which we'll say is right here, or at the reference point, which we'll say is right here, the moment of inertia about this axis is going to be the same, because the reference point and the center of flotation lie on the same axis. It's the other axis that really matters, because if you put your axis here, then all of this area has to rotate around this axis, and you'll get a specific value for your moment of inertia. However, if you place your moment of inertia axis here, you'll get a different value, because you're only looking at an area on one side of the axis.